evening, everyone. Welcome to HackNITR 3.0. The session is solving deep tech problems with open source workshop. And HackNITR 3.0 is here to give a plethora of fun events, workshops, and a 36-hour hackathon for hackers all around the world. We have around 2,000 registrations till now, and a lot of our audience here are building awesome stuff about a lot of separate problems. And I'm sure this workshop by Rosni Viswas and Anurag Sarar sir will help them a lot to learn about the open source. And now, before getting started with this power packed, insightful session, let's know more about our today's speakers. So, Rosni ma'am and Anurag sir both are the co founders of Wikilimo, who is they started to further climate resilience in vulnerable communities through data driven solutions. Now, talking about them individually, Anurag sir is an NITR Electrical 2017 alumni and currently working on quantum optimal control, developing tools for automated device bring up of superconducting qubits in the open source project and pursuing Master of Science degree in quantum engineering at Saarland University, Germany. And he was the co-founder and head of technology and product at Hamlet. And talking about Rosni ma'am, who is the NITS CS to 2018 alumni, she is currently working as a software engineer in the knowledge systems group at the Dana-Farber Cancer Institute, where she works at the junction of the computational and biological sciences, building end-to-end software tools that facilitate the use of data sciences to advance healthcare technologies. Prior to this, she studied metagenomics of microorganisms sampled from the International Space Stations at NASA JPL's Planetary Protection System, Planetary Protection Center. So I guess that's a short, brief intro about both our today's speakers. Now over to you, Anurag sir and Rosni ma'am. You can get started with your session. Thank you.
Hi, Swagat. Thank you so much for the really nice introduction. And again, thank you so much, HackNITR, for inviting us. It's, of course, always really nice to come back to the Institute, well, albeit virtually this time. But yeah, I think I just want to take a moment to appreciate how fantastic this whole HackNITR session looks like. So I'm given to understand that this is the third time that you guys are organizing this, and this looks so professional, so well organized, so well coordinated. This is like totally different from the hacking culture that we had in college when we were back there, I don't know, 4 or 5 years back. So yeah, this is really very, very inspirational to see that somehow through some internal or external impetus we have been able to drive the hunger for open source development on our campus, because well, none of this existed when we were back there 5 years ago, right, Roshni?
Yeah, even being a student of computer science, we didn't have a proper coding culture, or even like there were very few technical clubs that we could get involved in. And hackathons were like unheard of at all. It was only after I moved to the US that I got to know about like MLH Major League Hacking and attended a few hackathons, which were like 48 hour, 72 hour, and building real things. So yeah, it's great to see that NITR has progressed, and thanks to like kudos to all you organizers for setting the stage for this. Yeah, so like Anurag, do you want to just introduce yourself briefly once again, and then we can talk about what we are doing right now and how we got here and so on and so forth.
Yes. So I think this introduction will be more to sort of give you guys a bit of context about my background and how I got to doing what I'm doing right now. And maybe I could talk about some of the mistakes I made so that you have the chance to not make those same mistakes. So as Swagat mentioned, I studied electrical engineering in college, and well, studied because I didn't really spend a lot of time, spending in the classes. But that also meant that I got a lot of free time to develop my extracurricular interests, which at that point involved a lot of debating and a lot of work with Monday morning. But so I do believe, I wish that going back I could spend a lot more time also working on the technical aspects. But I was quite lucky that I got to work with some fantastic professors during my summer vacations. So I spent two of my summers working in Bangalore in a quantum computing lab. And for me, that was like a completely life changing experience. And I say life changing because back in our university, we did not, and still think we don't have any culture of quantum computing. We don't have any research in quantum computing, neither do we have any student groups interested in that. So for me, that really was pivotal in getting exposed to a whole new field. So I think I always encourage all my juniors to spend time doing internships, because you have to face it that you can only learn so much through your classroom and through your lectures and through your laboratory work. And internships are very, very important in developing not just an expertise and a niche for yourself, but also understanding that what do you like and what do you not like. So I also spent one whole semester in Japan working in a power electronics firm. And even though that was cutting edge R&D in Japan and everything, I realized I don't like that. As much as I enjoyed Japanese food and Japanese culture and being in Tokyo and all of that, I knew that I would never want to work in power electronics R&D. So yeah, I don't think I would have known that simply because, well, I just took the courses or the lectures and such. So yeah, it's important that you do internships, not just to get stuff on the CV, but also to know that, yeah, okay, this is definitely stuff I don't want to do for the rest of my life. But so these internships gave me the exposure that I needed in quantum computing. And I followed that up with a stint in Singapore, where I was working in, again, a university research center, working on quantum computing, but this time in a more hands-on approach. And that actually led me to my first stint in a quantum computing startup. So that was a totally different experience, and which again brings me back to the same point about why you should do internships, so that you should know what kind of atmosphere do you like working in. Because working in academia versus in uh, working in a public sector undertaking or working in a startup, all of them have vastly different experiences. And you could be doing deep tech in all of these places. And I think deep tech is like the common thread in today's discussion for Roshni and me. And it's important that you understand that just thinking that, yeah, I want to work in really hardcore research and development is often not adequate, because you need to also develop that feeling that, do I like doing that in a startup? Do I enjoy doing that in a government firm where things are more steady and well, or do I just want to work in academia? Do I want to pursue a PhD and become a professor, become a researcher? So yeah, my experience working in a quantum computing startup made me realize that, yeah, I probably prefer this startup culture more than any of the other working environments that I have been in so far. And that is what we have been doing over the last couple of years. Roshni and I have been working on Wikilimo. We have been building different solutions. But yeah, so I work in a field that is sort of still translating from science to engineering, which means you need a very high level of deep expertise, which is why where I am right now, I am completing my master's on the side while still continuing my day job, because you eventually need that sort of higher education to excel in this field. But yeah, that's where I am. That's why I am in Germany right now. And maybe Roshni can tell us more about why she is in Boston right now.
Yeah, so I'm a computer science graduate from the 2014 to 2018 batch. And it's been a ride. Like, I really fondly look back at my days in college, and I now, looking back, like, it's been a couple of years, and I can see how I have evolved both as a person and professionally because of all the experiences that I got. And I also really vibe with you on what you said about, like, making all the mistakes that you can at very early stages, because I also sort of did that. Like, I would say that I'm a late bloomer, and going into college, I didn't have it all sorted. Like, I didn't know that I'm going to do like research couple of years down the line. I'm going to be at NASA doing multiple internships, or like, I didn't have it all figured. And so it was trial and error. It was trying out different things, working on different projects, working with different people, and like figuring out what exactly I want to do, and it wasn't easy. So like when I came into college the first year, I had a terrible GPA, and I was like, oh, everybody was like, oh no, like how are you gonna improve this so that by the time you're in third year or when you're in fourth year, you'll get placed at the best companies, or you'll be even eligible to sit for placements or internships and all that. And I was like, oh no. But then yeah, like slowly I understood that I have to kind of strike a balance between all the different things that I want to do. Very early on, I had a passion for biology. Like even before I got into college with like deciding my major in computer science, I always knew that I had a interest in biology and I wanted to pursue that. So back in our days, we didn't have a minor system like you guys do in NITR now. So like if I could back then, I would have gotten a major in computer science and a minor in biology, and I would have been all sorted. But I wasn't able to do that, so I strategically tried to take open electives from the LS and BM departments, and tried to get internships in bioinformatics, which is the intersection of the two fields of my interest. And so like in my second year, that actually wasn't possible. I wrote to hundreds of professors working in bioinformatics trying to get an internship in the field, but I didn't. Honestly, I worked in something else. I worked in like image processing, and worked in like music and like all sorts of different signal processing aspects. But I learned a lot about data science and stuff like that, but I couldn't get into bioinformatics. And then like third year, I tried all over again, like looking at what all internship opportunities are possible. And my GPA was always a hindrance to that, because most of the awesome like internship programs that take you abroad and get you to work with like researchers who are doing cutting edge work, they require you to have to show very strong academic potential and good grades, which I didn't have. So again, that was a very big challenge for me. But it all worked out somehow. Third year of college, I got through the Caltech Surf program, and that is one of the few programs which actually do not have a very high GPA cutoff. And so I was able to land my first internship in bioinformatics, and um, for the first time got to see what it's like to work in a like a research setting, and like get my hands dirty on real bioinformatics data. And yeah, that was great, and so kind of opened a lot of doors for me. They always say that like the first opportunity is the hardest to land, and I think that is very true, because once you have something on your CV, even though my first internship wasn't the most coveted one, I saw that like you capitalize on what you have to get better and better. So like you start low, but then you totally like slowly climb the ladder. And from the first opportunity to the second, after my first internship at JPL, I landed a couple more internships at NASA. They were all at different research centers. So I worked at NASA Ames Research Center, which is in the Bay Area in California. Then I worked at NASA Langley, which is in Virginia, and all on different projects. So like some of them were in earth sciences, biospheric sciences, data science, working on machine learning and AI. And I got a very varied skill set that gave me a flavor for all the different things I can do with a versatile computer science degree. And so now that I had everything that I needed to kind of make a decision before my first job, I kind of went for it. Like I knew that it was all tried and tested during my undergrad. So when I had a couple of offers from different labs, and there was one computational biology lab where I am right now, which is in Boston at the Dana Farber Cancer Institute. We are kind of in the intersection of academia and industry, I would say, because my lab is closely affiliated with Harvard Medical School. But at the same time, we work on projects that are funded by the pharma and biotech industry, working with various different similar cancer research hospitals and biotech firms across the US and in different parts of the world. So yeah, I've been at this job for about 1.5 years now, and I've learned so many different things. And at the same time, I have also been able to work on Wikilimo, which I co-founded with Anurag, 1.5 years ago as well. And so yeah, it's been great, like building and working on different things side by side. Um, and again, like I don't know what's going to be my next step, but so far it's been uh, Great ride. Yeah.
Yeah, I think on that note, like maybe we can spend the next, I don't know, couple of 10-15 minutes talking about open source aspects in our work. So I'll tell you a little bit about the open source that we do at quantum computing, because like my day job involves maintaining a moderately large open source library that we use for different quantum computing applications. And then Roshni can try to sell why you should be doing bioinformatics instead. And then we'll tell you also about the open source stuff that we do for our climate informatics project, Wikilimo. Okay. So most of you have probably heard of quantum computing. It's difficult to not hear about it with the constant media hype and news and everything. I think I should give a disclaimer at the very beginning that we don't have, commercially useful quantum computers yet. Don't believe any media article that you read that says that quantum computers have solved COVID problem in the next 6 months or anything like that. We won't be having a commercially useful quantum computer at least for the next 5 to 7 years in the minimum. But that means I have a job. Why? Because my job is to make sure that the bad quantum computers that we have right now, we can make them work well. And what I mean by that is I work in the calibration. So most of you here have a sort of engineering background, and you know that you often need to calibrate tools, devices, and calibration means that you need to characterize a certain device and you need to have certain properties about the device so that what you expect of it and what it actually does in real life are in sync. So you have a certain piece of metal or like a length of metal, you expect it to be 1 meter long, but maybe it is 1.1 meter long. So you need to calibrate that, okay, this is actually 1.1 meter long and not 1 meter long. So we do that for quantum computers. And what I mean is that, so we have these quantum devices. Many of you have seen this really bright golden fridge that has all these nice golden wires coming out of it. Well, that's not a quantum computer. Again, I need to break these myths. That's not a quantum computer. That's one of the electronic components that are used for controlling quantum computers. The actual quantum computer is a very small device, maybe this small a bit, that stays at the very bottom of that fridge. But yeah, so where does open source come in this picture? Open source comes all across the quantum computing stack. And I'll be talking about a few of these. And maybe while I talk, I'll also point you to resources that you can look up if you want to get into quantum computing and take the open source route to quantum computing. Okay, so I think first up, the most common approach for people to get into quantum computing through the open source route is to learn something called Qiskit. So Qiskit is Qiskit. It's a very nice Python framework that lets you work with quantum computers right from a very abstract level to a very low level. And what I mean by abstract level to low level is that if you remember your first year, electronics, or your first year computing 101 course, you would know that we have this digital electronic part, these transistors and everything at the low level, and at the very top level we have the algorithms. And the thing with quantum computers is that right now, because they are so crude, a lot of work gets done at the transistor level instead of the actual algorithms level. But that's a good thing. That means you have more fun things to play with, because, well, in classical computers, almost all of the transistor level stuff is so perfected right now that we don't even think about it for most of the time. But right, so coming back to Qiskit. Qiskit is a fantastic framework that you guys can get yourself into. It's a good introduction to quantum computing. It's a good approach to learn what quantum computing is all about. And it also lets you understand quantum computing right from the very top level, understanding how the algorithms work, how the computing part of it works, to the very low level to understand what is quantum about it, what is the physics behind it. So one of my day jobs, or one part of my day job, involves designing frameworks or modules for Qiskit. And what happens, I think again I can take an analogy with the classical computers. So in classical computers, like you'd have chips from Intel, AMD, or maybe Qualcomm, ARM. Apple uses ARM chips these days, right? So you have all these chips, and you have a lot of stuff in between, and then you have either Windows, Mac OS, Linux, whatever is your flavor. But in between, you have a lot of stuff, and oftentimes we don't even think about this stuff. And this is the firmware, and that's what I build for quantum computers. I have to build firmware for quantum computers so that we can drive all these nice algorithms that somebody would write in Qiskit on these devices. So yeah, if you are somebody who right now enjoys embedded Linux, who enjoys writing embedded software, maybe we should talk, and maybe I can encourage you to pursue the path of quantum computing, because right now in this field we need a lot of people who enjoy writing low level software that is interacting much closer to the hardware than, I don't know, a machine learning pipeline, for example. So yeah, so that's one part of what I do. Another part of my work involves what I was describing previously as the calibration tools. So calibration tools, maybe those of you in the audience who have an electrical or mechanical engineering background, who have taken control systems courses, so that's a big part of the software or the algorithms that we develop. So if I look back and recollect, I think the control systems that we used to get taught at NITR back in 2014-15 was still quite archaic, for the lack of a better word. But control systems is a fantastic field right now. It's a very interesting field because, well, a lot of the stuff that you do in machine learning has its roots in statistics and control systems. For example, reinforcement learning, if you look back in literature and history, a lot of it is in control systems. So I get to be in this really nice position where I get to play with control systems algorithms that use reinforcement learning to work on quantum computers. So, all the buzzwords in one sentence. But yeah, if you think that these topics sound really nice to you, then you should definitely consider quantum computing as a field that you should pursue, because all these things that I'm mentioning, so for example, Qiskit, then this reinforcement learning approaches to using quantum computers, or the calibration tools, the firmware, all of this that I develop, all of it is open source. So like maybe I can share a more personal anecdote to how I got into this whole field, the whole field of open source development for quantum computing. Because when I pursued quantum computing during my undergraduate years or during my initial time in Singapore, that was none of that was open source. And I got into it because I read a post on Reddit. So I read a post on Reddit about how a new university group was starting a new open source project. And I contacted the person on Reddit, and they were like, yeah, sure, let's do this. And then we set up a call, and then I started working with them. Like, that's it. All of this happened in 2 weeks, and I had not met them before that. In fact, I had not met them until like a week back. So the first time I met this collaborator that I had been working with for the last 3 years was a week back. So that's kind of, I would say, the power of open source, because we could have such a fruitful collaboration for 3 years where we could get multiple papers written out and submitted and published, all without ever meeting each other, and all because this entire science and entire code and entire software was open source that we were developing together on GitHub. So yeah, like I have a lot that I owe to open source, because like my first publication came out of open source. My master's was driven by open source development. My research is driven by open source development. So yeah, like for me, this has been a very, very rewarding experience. I think when we talk about open source, or a large part of the open source projects that we see online are somewhat software centric, which might lead most people to believe that, well, open source is not something you do if you want to do really hard and really deep technology focused things. And that is not true. Like the fact that we are doing quantum computing, or Roshni is doing bioinformatics, which are some of the more science heavy fields, and our day-to-day work involves writing open source software, that in itself means that if you think you want to do really hard science, and you also want to do open source, those things need not be completely disjoint. You can be at the junction of those two things and still be completely fine. So maybe, yeah, this is probably a nice time for Roshni to explain how she incorporates open source in the bioinformatics stuff that she does.
Yeah, so at the Dana-Farber Cancer Institute right now, I am part of a group called the Knowledge Systems Group, and the project that I'm working on is a cancer research project focused on immunotherapy. So my team is called CIDC, Cancer Immunologic Data Commons. We are building a data commons that integrates data from all of these immunotherapy clinical trials that are going on for the past like 5 or 6 years all over the world. And we are building, like my team is a software team. I don't work in a biology lab that does like bench work and actual experiments that you see. But we build software, and software is really necessary even in biology labs, because without proper mechanisms to share and store and share and query all of the data that your biological experiment is generating, the experiment has very little value for large scale analysis. Because like these days, with new technologies in biotech like next generation sequencing, the amount of data that these machines generate is like terabytes and petabytes of data, and it is no longer possible for a biologist to load your data into Excel or any like little spreadsheet like that, or any small piece of software that is unable to handle that large scale data, to actually analyze it in a way that it would be reasonable for translational applications. And so so my team is responsible for building these ETL processes, building web applications, building APIs, so that when we have a huge network of cancer research centers working together for a common goal, we are able to automate the storage and sharing of all of this data. And so in particular, we are focused on immunotherapy and focused on immuno-oncology actually. And what this means is like we study the kind of treatments that take advantage of the body's immune system to fight cancer. And it's a very unique and up and coming field in biotech. And like I would also go to say that this is kind of groundbreaking, because there are other therapeutic ways like chemotherapy as well, but then those are not as like there are many advantages of immunotherapy because of the way it works, and the body's immune system is able to recognize certain cells and like cancerous cells and remember what it looks like. So in general, it is far better than the kind of side effects that chemotherapy might have had on your body. And so now that immunotherapy is kind of picking up, and now there are so many clinical trials going on that test drugs, immunotherapy based drugs. Uh, our particular project is a NCI funded moonshot, which has a long term goal of doing cross trial analysis from immunotherapy assays. What this means is that you have what we used to have in the past is you have clinical trials going on at different like labs and centers. But what we are aiming to do is pull the data together and build a data commons from multiple of these clinical trials, and to analyze all of this data together on one single platform. So while this is all like sounds great because you have all of this data and it's combined and it's like a big large scale operation, at the same time it has a lot of challenges. And the biggest challenge, one of the biggest challenges, is scalability, because we have never seen or worked with this scale of data before. And one of the solutions to that is like cloud computing, because you can no longer do local analysis on your own laptop for the data that you have. You kind of need to spin up clusters, you need to spin up virtual machines and do all the data processing on the cloud. And that is why some of the biologists that are not trained in computer science need people like us, who are trained in cloud computing, who are trained in building large scale like software engineering applications that can handle these kind of experimental designs. And like our stack that we are building is kind of like a full stack engineering operation, where we are able to integrate all of the experimental designs, all of the data, and kind of scale it in an automated way, where you can ingest all the petabytes of data into a cloud based database. So we use like Google Cloud Platform for everything. And we are able to, now we are at a stage where we are able to remotely access and query everything from the Cloud SQL database that we have. And so not just like, so all the code that we write in my team is open source. Everything is on GitHub. You can go and access it and you can see it. And not only is the code that we write on open source, a lot of our code base like has dependencies from open source libraries, and some of these libraries are actually directly focused on biotech. It's not just that we are using some generic data science framework that's out there, that those are the kind of libraries that are very, very popular in open source, but we also have very niche scientifically focused libraries that we are able to use. And these are uncommon. These are not very heard of, and like you might not know about a lot of these because they are not as popular. When you try to, like, if you go on GitHub and you try to find places to contribute, a lot of times a lot of the more popular repositories are highlighted because they have like all the good first contribution tags and all of that, so it's easy to find them. But if you spend a bit more time and you look at scientific organizations that also promote open source science, then you will find, if you're interested, I can also point you to some. You will find very niche scientific applications in these fields as well. And so yeah, like I also have a lot to owe to open source because the entirety of my job is promoting and encouraging open source development, which is up and coming in science. And now, like, my project is a publicly funded, it's a NCI funded trial. So now we, like, for publicly funded science, something that is still like, there's a culture shift that's going on. Science used to be not as inclusive as it is now, but now with open source, it's becoming much more transparent, much more accessible, much more inclusive, and also reproducible for everybody. So now, like, reproducibility is one more thing that I want to talk about because in the past, people would do localized scientific analysis on their own computers. And one problem that we have faced, particularly in biology, is that a biologist would spend hours and hours to run somebody else's code and do analysis. But now, with open source and with all the kind of like new version control and like continuous integration systems that we have, this has enabled us to really promote reproducible research. And so now the research that I'm doing can be accessed and redone on somebody else's computer somewhere else in the world. And that has really been possible only because of open source. Um, yeah, like, do you want to talk about Wikilimo now, maybe? Like, now we have covered quantum computing and bioinformatics, and I feel like the the third thing that we've been working on and working on together kind of needs to be talked about as well. So,
Yeah, I think there's
yeah,
also
over
a
to you.
question in the comments, and it seems like it's the last question that has, like, or the latest question that has come in. So we'll start from the back, and it says, "How did you think to build something like Wikilimo? What were the difficulties you faced during it?" So great. So this will be our motivation for the next 5-10 minutes that we tell you about Wikilimo and how Wikilimo uses open source, open data for solving really hard problems. So, really hard problems. What is the really hard problem that we are trying to solve? The really hard problem that we are trying to solve is climate change. Just kidding. That's not what we are trying to solve. The hard problem that Roshni and I are trying to solve is that because of climate change, there are a lot more adverse weather events that take place these days. And by adverse weather events, I mean much more severe drought, much heavier rainfall, and a lot more flash floods and completely unforeseen tropical cyclones, things like this. Adverse extreme events that were previously far more rare are not so right now, and climate change is to blame. That's not even something that we're debating or discussing. Uh, what can we do to solve this? So the broad field that this lies in is the field of climate resilience, which I believe is something that engineers are primed to dive into. Why? Because the core tenet of climate resilience is that, um, let's assume human beings are not able to do enough to stop the adverse effects of climate change that we expect to see over the next couple of decades. What do we do in that situation? Well, you turn to engineers so that they can have some solutions to these problems. And that's the driving goal or motivation behind Wikilimo. That what happens if these adverse weather events that are now starting to get more and more frequent become even more of a daily occurrence? How do we fight this? One way to fight this is to have uh, a tool that can predict and that can give you actionable insights about these events. Now, what does that mean? That means that, well, let's accept that these adverse events are going to take place. The best you can do then is that you know in advance that this adverse event is going to take place so that you can prepare yourself. You can remove people from the coastal areas. You can issue warnings that there is going to be a very dangerous flash flood. Please stay indoors, things like this. So in order to make these predictions, you need to be able to model systems. I don't know if you guys know, but the Nobel Prize that was awarded this year in physics was for modeling chaotic dynamical systems. And one such example of chaotic dynamical system are climate models, because climate models are so complicated with such a huge number of parameters that modeling them requires far more complex analysis than you would for, I don't know, like modeling which next item you should watch on Netflix. So this kind of chaotic models, they thrive on data. So you need to have a lot of data that you can feed into these models to produce good quality predictions. The good thing is that we already have a lot of these really subtle and really well designed exotic models that can model our climatic systems, our complex climatic systems. Bad thing is that most of this knowledge, this science is restricted to a very few highly industrialized advanced economies. That is bad because, well, first reason is that such humanity saving science should not be restricted to only a few hands. But the even more relevant reason is that when we have climate change, the biggest, not when we have, now that we have climate change, the biggest impact that you see are on countries that are significantly less financially and industrially well off than their peers. So you see a lot more impact of climate change, for example, in India, Indonesia, other parts of Southeast Asia, in Africa, Latin America, than you would, for example, in Central Europe, so or in the US. So it's important to understand that the biggest impact of climate change is often on the least privileged nations, which means that these least privileged nations have an even greater need for these climate modeling tools and climate modeling science than do the much more industrialized nations. Because, for example, for somebody in Brooklyn in New York, they need to know that it's going to rain in the next 6 hours so that they can go and get their avocado toast but have an umbrella. But for somebody in India, it means that they need to go and protect their crops, and the whole agro-based economy relies on this form of really hyper local climate insights. Okay, so now that I have made you guys realize why it's important that we build these hyper-local insights, I'll give you examples of few such tools that Wikilimo has been developing over the years. So the very first motivation that we had was for hyper-local weather insights, and the customer or the use case for this were agro-based economies. And agro-based economies need long-term climate insights. What does that mean? That they need to know 8, 10, 12 months in advance what is going to be the expected rainfall for the coming year. Why? Because based on that, they can decide which crops to plant. Based on that, they can decide how they should irrigate their land. Based on that, they can decide if they need to plant drought-resistant crops along with the standard crops so that they're economically sound. And we have for the most cases, we have the data for this. What we do not have are the analysis tools. So this is something that we started off building initially. The whole open source climate informatics stack that can process data from satellites, data from radar, data from imagery, from land-based monitoring, that can churn all this data and produce long-term climate informatics insights. And an even more like interesting problem that comes up is that once you have this data, that's not just enough. You need to disseminate it. And what that means is that you need to be able to deliver this data to the last mile. And this last mile is not the house where you and I live. This last mile is often some rural agro based region which has vast farms and like very few, let's say, residents, or even if there are a lot of residents, there is very little connectivity. Well, at least in India now we have much higher connectivity, but that's not the case, for example, in the rest of Southeast Asia. So this last mile dissemination of climate informatics is still an open problem, and that's what we started working on: how to deliver these insights on a platform where, for example, you don't have a smartphone or you don't have 4G internet. All you have is a very basic feature phone that can only take voice and SMS. So even though most of what you and I use on a day-to-day basis are things that just assume that you have a smartphone with 6 GB RAM that can access internet at 4 Mbps all throughout the day. That's probably not true for a large part of the people that feed us. So yeah, so that's what we started off. Soon enough, we also got engaged with the European Center for Medium Range Weather Forecasts. That's a really long name. It's basically the Meteorology Department of Europe. And what we started off with them is how to predict wildfires. Now, wildfires again are something that you often read in the news, right? Oh, wildfire occurred in California, wildfire occurred in South Australia. Great, we hear about these places, but that does not mean that wildfires only take place in these places. Uh, Latin America experiences vast wildfires every year. There are very, very bad wildfires that take place in significant portions of Indonesia. Same for Africa. And we hardly even hear of these wildfires. And that's again because of the same reason. The whole wildfire prediction, wildfire monitoring, wildfire control techniques, science, engineering, these are restricted in very few advanced economies. And that's why we started working with the European Meteorology Department, who has a project to develop these open tools, these open source tools, mostly machine learning driven, that ingest a lot of satellite informatics and data from ground based stations to predict wildfires. And this was a fantastic experience for Roshni and me because we spent a lot of time developing the technology stack. So for the previous problem that I was describing regarding disseminating the information, it was more about building existing tools together to stitch together a coherent solution that can be packaged and delivered to remote communities. But here it was more about building the real science and the real technology stack of how do you predict wildfires from data on rainfall, humidity, biomass, and such things. And we learned a lot about using various classical as well as deep learning techniques that can be used for this. So this was beyond the open source part. This was also a very scientifically rewarding experience for Roshni and me. And yeah, so somebody else has also asked that if we plan to continue to build such projects at Wikilimo. But yeah, that's the idea. That's what we have been working on over the last couple of years, that we continue to tackle such problems that maybe already have some form of a solution, but the solution is not widely adopted, or it is only restricted to very, very few communities. Because I think this whole motivation is driven by the concept of inclusivity. And the whole concept of inclusivity revolves around the aspect that science needs to be inclusive for all. And there is no better way of doing that than making science open. And when I say science, you might be thinking, am I talking only about publication papers? No. Software is as much a part of science as anything else. And I think Roshni wanted to highlight how open source is an important aspect in open science and reproducibility. Do you want to continue, Roshni, on that?
Yeah, absolutely. So I think that I want to highlight that, like, now with the advent of open source, the barriers to innovation are really crumbling. Like, anybody who has access to internet and a development environment can contribute to open source and take part in science. And science is not just restricted to institutions and laboratories that have that infrastructure to do so. Like, now, with just the setup that you have at home, and now with COVID and everything, people are becoming like, there's a shift, and people are becoming more and more inclusive to people from very remote environments participating in science. And so we have gotten to work with scientists in various different fields, in biology, in quantum computing, and climate informatics. And some of the common themes that I have seen repeating is that a lot of scientists are not actually trained. They lack the formal training in writing software engineering code. And me coming from a computer science background and having taken like actual software engineering coursework during my undergrad, and even after that, I see that like there are certain best practices that are involved in scientific applications, which are often missing. And these common themes are things that I would really encourage you all to pick up, because you will find it useful in general in so many different aspects. Like if you don't have the best practices in any application, it is often a hindrance to reproducibility, to like so many different aspects of the performance of the code base itself. And so really, I want to emphasize on picking up those coding best practices, no matter what engineering discipline you are studying in college. Whether you are in electrical, electronics, computer science, even biology, doesn't matter. But code and software is becoming integral to any kind of scientific application. And so really pick that up in your free time and participate in these kind of hackathons, because uh, you get to work with people you'll get to work with people even during this hackathon, who are coming from different engineering disciplines. And also even within computer science, like you'll typically in a hackathon like this, you are in small teams, and you'll have like some person working on the back end, some person working on the front end, somebody doing the database. And so these kind of skill sets are usually complementary to each other, and it is often hard to be adept at all of these different things. But in a short span of time, in a hackathon like this, you get to pick up a lot of things in all these complementary aspects. And so I would encourage you all to participate in as many hackathons as you can, not just this one, but there are so many hackathons that are like on posted on MLH and DevPost and so many different platforms these days. Go and, like, it's hard, but put yourself out there. Just like team up with people from different parts of the world working on different things, and you will really learn a lot in short spans of time. um, Anything you want to add, Anurag?
Yes, so I think I have also like a bit of a like personal anecdote to add to the whole aspect of inclusivity. So I work in the field of quantum computing, and one of the good or bad things about quantum computers right now is that they're very expensive, and they're like prohibitively expensive to the point that we don't have one in India. So like so many countries around, well, not so many countries, but many major economies around the world have quantum computers, and we don't have one in India. And one of the prohibitive reasons for that is that the all the different parts of the quantum computers that come together to make one whole, we don't make any of that in India, so it would all have to be imported, and it's just prohibitively expensive. Now, why is it prohibitively expensive? One of the reasons for that is because all of the technology is locked up either in universities or in companies that are not based in India. Which means if somebody wants to build a quantum computer from first principles, as in read the science, find the technology, build it themselves, they can't do that. So that's actually something that I am working on right now with collaborators who are based all over the world. Many of them who are currently maybe in the US or in Europe, but originally come from lesser well-off countries, who understand what big of a mess this is. That if tomorrow or if 5 years from now quantum computers exist, and not if, when they exist they will be really powerful, and if you only have them in like 4 or 5 countries, do you realize like the kind of inclusion access that creates, and like the problems that creates? So we are working on creating a full open source stack, And I think this addresses another question somebody asked in the chat, which was, what exactly are deep tech problems? As a fresher, where can we get opportunity to be involved in this actual awesome stuff? So what are deep tech problems? I think to answer that question, it's a very simple answer. It's that anything that looks like it should be more science and less engineering is probably deep tech. And what I mean by that is, if you see something or if you read about something that looks like, oh my God, this definitely sounds like science fiction, chances are it's deep tech. And that's a very good rule of thumb you can use, right? Like stripping up your DNA to introduce something inside it as a medicinal property. That sounds like science fiction. That's stuff that you'd see in movies from like 10 years back or 15 years back. But that's deep tech science that's happening right now. That's CRISPR. So this sort of gene editing techniques, one example of deep tech. But in general, why I'm talking about deep tech right now in this aspect is because when you are building stuff like quantum computers or cancer treatments or vaccines or climate models, things like these, they often have a very significant science and research aspect to it. And if that is something that you enjoy, then deep tech is definitely for you. And this is not like a whole good and bad question, right? Because oftentimes I have had other friends and colleagues in deep tech who have this air of superiority that, oh yeah, we are doing deep tech, so it's definitely cooler. That's not the case. Let's be very clear that these are just two different aspects. It's as important to build better software and better apps as it is to build, I don't know, the next quantum computer or something. But if this is something that excites you, where you don't mind that things will not always work, where you don't mind that you might have to read a lot of research papers to understand something and not just blogs on towards data science, if that's something that you like, then deep tech is definitely for you. So for example, what am I doing right now with the whole open stack that I was talking about? So making a quantum computer means making a lot of things. First, you see those golden stuff. Those are the fridges. We don't make them in India. There are companies that make them in Finland. There are companies that make them in Oxford in the UK. So at some point, India needs to learn how to make them. Not just India. At some point, the rest of the world needs to learn how to make them. Otherwise, this technology will forever remain integral to one part. Then you need a lot of the computing stack. And this is, well, some of it is classical computers, like the computers that you and I have at home. Some of it is slightly more configurable computers, which are FPGAs, or more embedded software. And this part, again, it is locked into a few companies that exist in Europe and US. We don't have any companies in India, for example, which are building firmware for quantum computer controllers. And the next part are the actual quantum chips, which are basically semiconductor manufacturing processes. Again, something that you do not have in India right now. So these are all deep tech problems. These are all things that can be solved with open source, which would make the world a better place if we solve them with open source. Now the question comes that how do you get an opportunity to be involved with this? Somebody also asked, I think in another question, that how did we get started? So I think both Roshni and I have already pointed out how we got started. Well, for me, it was purely just like, keep an open eye and keep an open ear. And when you find something interesting, work on it. But how do you do that when you're in your first or second or third or fourth year of college? How do you get into the whole open source for deep tech regime? I think a good starting point often is that you have to build a sort of hunger or appetite for research literature, which means that you will have to read research papers as normal stuff. You don't leave a research paper for, oh, that's like something I don't enjoy reading. Oh my God, the professor gave this to read again. No, if that is your general impression of research, then maybe deep tech is not something that you will enjoy a lot. So that's one approach. I think that's a good starting point, because oftentimes when you will read many of these research projects, you will see that they talk about a problem, they talk about an implementation, but they don't include anything that they show the implementation. And you can always start small. You can start from if you're somebody who enjoys machine learning, you go and read the original convolutional neural networks paper. You read the paper, you see that they talk about CNNs, but they don't talk about anything about how to do the implementation and all that. So once you start this whole habit of taking a paper, a very simple paper if required, understanding the implementation in it, and then writing the software for that implementation, congratulations, you have already done open source for deep tech, because that is exactly what you will be doing in your day-to-day job if you want to build open source for deep tech. That's what I do. Like, we have papers coming out from collaborators, from people all over the world. We'll sit down, we'll see, okay, these people did some really cool stuff, this looks good. Shit, they did not include the code. Okay, let's go to the, so what do we do now? We sit down and we start writing the code to implement this. And when I say code, I use that interchangeably for open science and open research. And I think it's fair to use the word code for that, because in today's world, uh, code and software really is important. Like, you should be learning it the way you learn high school math, the way you learn calculus in school, in college, the way you learn, I don't know, like basic stuff. So software and code should be included in that basic skill set that you have. It does not matter what you are studying. It does not matter if you study economics, does not matter if you studied biology. You will need to write at least 10 lines of code at some point, even if it is just for, I don't know, if you're an author and who wants to write a book, you will need to write it in LaTeX because your publisher will not take it otherwise. And that's code already. So in today's world, it's fair to use code as a placeholder for, open stuff. But yeah, I think that's a good way. Take that approach. If you can't, find out such simple papers, there's a place called Papers with Code. Like, literally, the name is Papers with Code. Go to paperswithcode.com, find a paper, write your own version, then compare with the version that already exists on there. And yeah, like, as soon as you start you do this twice, I think you have already done more than what most people of your age group have been doing. And if you do that, you can already, like, and again, this is not just for fun, for hobby. For those of you, who are more, let's say, career minded, if you can really show on your CV that you have a GitHub profile where you have implemented 2 papers, I can assure you personally that you will have a very good chance of getting hired. So yeah, that's already deep tech. And for those of you who are not into machine learning, for example, well, there is electronics. So much of the work we do in electronics right now is writing software to design better components. Same for biology. So much of the work you do is writing software for doing better experiments. So every field will have a part where you can take a paper, understand the software implementation, and write your own version of it. And that's a fantastic way to get yourself onboarded into open source for deep tech. Okay, I think Roshni and I have already exhausted all that we had to share. If there are more questions or questions that we missed out, or any of the organizers want to ask something, I think we are open to answering them now. You are muted.
Okay, my bad. Really sorry. Yeah, it was a really cool, insightful session, and some of the points that you shared about be that open source or in general computer science is something that we believe as well, right? Computer science has grown so much into everyone's life, and these days everyone wants to go into CS, but everyone forgets that point that whatever your branch is, CS is already there. Like implementing that along with CS is something that everyone should look for. So that has been something really good. And coming on to the open source point, I like being a student of NIT Oracle, I do want to share with you that the open source culture has grown tremendously at NIT Oracle within the past 2 and 3 years. We have had different clubs who are actively engaging into communities, and this entire hackathon has been done by 2 clubs, that is DAC NIT Oracle and Open Code, which are very much open source prevalent organizations. And as a part of that, like we have this institute counseling services, which you may know. So DSC has went ahead and created an application for them to handle their operations completely, and it is completely open source. To this point that it was even featured into Google Dev Library, and we have had some really phenomenal contributions from all over the world. So yeah, it's growing pretty good.
I think
So happy
somebody.
to hear that.
Yeah. Go
Yeah.
ahead, Roshni.
No, I just wanted to say that I'm so glad to hear that. Like that is something that I wish we had during our time, but yeah. Kudos.
Yes,
slow
I
and
think
steady, but yeah.
it's like the very ideal scenario when, like, in-house developers are building the software apps for the institute, and we don't hire TCS and Wipro to build a very shitty website for the institute. So yeah, this is fantastic. I'm so happy.
Eventually, yes, that is the plan, that students are the ones who are empowering the institute as well.
Hmm.
So yeah.
Yeah, I think somebody asked if code contributions are enough to leave an impact in an open source organization, or should one also focus on other factors like community bonding, etc. Okay, so I have a bit of a controversial take on in this. I believe that code contributions should always be the first thing that you do when you want to contribute to an open source. I have seen many people who are really into community bonding and community building and platform building. Maybe that's your thing, maybe that's your jam, you do you. But to develop a long lasting impact, I think if you start the path where you make code contributions, where you make genuinely strong, significant contributions, that also gives you the backbone that you need to fully understand that ecosystem and that platform before you start to onboard people and become the community champion, or whatever is the term these days. So yeah, like, take that approach where you build that solid foundation before you dive into the more people approach. And I think this has also worked, not just for this case, but it also works in a professional setting. If you are somebody who has a very strong technical foundation of the stack, the platform, the project, anything, you have a much easier time in dealing with people. And I think that's often what separates engineers from, let's say, somebody who directly takes the path to becoming managers. When you are a manager who has been in the trenches building software and fixing bugs late at night, you know what it means to be in that situation. So put yourself in that position first before you try to deal with people.
A very well answered question actually, and this does arise quite a lot. Like you have the community building aspect as well, and actually making contributions, and this sums it up pretty well actually. So yes, I remember Roshni ma'am talking about MLH and everything, and again a quick plug. But yes, HackNITR does have MLH as a partner, and it is a phenomenal community. So yes, we are growing in all aspects. Again, thank you so much, sir, for like being a part of Hack and ITR, and we are very much inspired from the works that you both have been doing. So thank you a lot.
Thanks for having us.
Thanks for having us. Bye bye.
Bye bye.
Bye.
Okay, people. Hello. I believe that was a really insightful session for each and every one of you. The initial submission is going to be live pretty soon. We'll get you all the details onto Discord as well. So stay tuned for that as well. Apart from the initial submissions, we are, of course, going to have a mini event today as well. The details for the same will also be given into the hashtag mini events channel. Keep an eye out and do make sure that you fill the form circulated today around at 8 p.m. I believe it will be circulated within 5 to 10 minutes. You fill the form within the end of the day. Cool. I guess that is it. See you then. Bye bye.